Exercise 41.4. The exercise is to be solved with the assistance of the TI-Nspire CX CAS version 3.2. Consider the region bounded by the graphs of y equal to 5x squared minus 49x minus 49 and y equal to negative 4x squared plus 29x plus 27. Part A. Provide a graph of the region. Part B. Provide a graphic approximation of the area of the region. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Part E. If able, obtain an exact value for the area of the region. Alright, Part A. Actually, as a first item, I would like to take a look at the calculation mode and the number of digits that is set right now. So let's go to Document and Settings and the Document Settings. Alright, in this particular exercise, the one time we have a requirement for approximation is the part C, which requires a 5 significant digit output. So maybe we plan for that by floating 5 digits in the displayed digits right now. The second item I generally look at is the calculation mode. Right now it's in auto. Auto is good. Auto means that whenever the calculator receives inputs that do not have any decimal points, that it will try to provide an exact result. If the result is not concise, then it will not record an exact result. It will provide a decimal approximation instead. Alright, so let's click OK here and go to our first page. And for a problem like this that has many parts, I think I like to have a first page be a note page that provides a summary of the solution. So for the menu, I will click 6, Add Notes, and start off by titling this as a Exercise 41.4 Solution Summary. And Part A, I will already write a little thing about this. I'll say that a graph of the region is on page 2. Okay, another thing I think I'd like to do, this is sort of the title of the document, so I think this deserves to have bold font. So formatting the text, go with bold. I wonder if 12-point font would even look better still. Yeah, I think I'll go with that since it fits without having to wrap to a second line. Now, let's get a page 2 going and work on the graph. So Control, Add Page, Add Graph. Alright, got a graph and the entry line is waiting for us. Looking at those original equations provided, we'll have here a f1 of x equaling, we'll call it the 5x squared minus 49x minus 49. Enter. Well, okay, one segment of that parabola appears. Don't worry about that for now. Let's go hit Tab and input our second equation. This is the one that has the opposite of 4x squared plus 29x plus 27. Enter. Okay. Now we need to find our enclosed region here. I think I'll start off by pulling in the axes. Now we do know from inspection that each graph is a parabola. Okay, we have to go quite a ways out and okay, I'm starting to see something now. I think at this point I'm going to go to a zoom box. Menu, Window Zoom, Zoom box. Let's see, at first maybe I'll just try to obtain an enclosed region, then I'll get a little fancier with a second zoom box, I think. First, let's try that. Actually, that looks okay. This is almost pretty good. I think I can provide a little more width to this enclosed region. So I'll go with a second box, starting, say, up here. Now I want to make sure I get the bottom of that second parabola. I'm going to give myself some room on the right so there's room for the labels and everything to be put without cluttering up the region itself. So I think right about there. Okay. Now I put escape to put away that tool. I'll start moving these labels into more appropriate spots. F1 blue label there. I think that would look pretty good. I'm going to move things over a little bit because I want to put a intersection point label on the left there. So let's just move it a little over here. There. This could go down here. Okay. Something else I want to take care of right now, and that's that these axes are, the scaling is awfully dense. I don't think we need to see so many scale marks, and I would like to have nicer looking numbers on the ends instead of things like negative 175.85. That's too clutterish, I think. So what I'll do is I'll go to the menu, and let's go to the Windows Zoom, and let's go to the Windows Settings. Clean this up so it looks nicer. X-min, okay, maybe a -9. Tab, X-max, I think 30 will be fine there. Tab, scaling, okay, it's, what is it, 39 units long. If I divide that by 10, it's about 4. I think I'll scale it every 4. That will look nice. The Y-min, okay, -175 would be fine. Tab forward, max, okay, let's call it 100. Tab, alright, right now that axis is 275 long. I suppose every 50 units would be a fine scaling there. Alright, let's click OK. There, see, it looks nicer, I think. A cleaner looking graph. Now, let's see. Things are shaping up. I'm going to do some shading now, I think. And for that, I am going to do this. I'm going to approximate this with a polygon. So menu, geometry, shapes, polygon. Alright, so do some approximating here. I find this is the best way to get a specific region shaded on the Nspire. If you try to work with inequalities, for which the Nspire will do some shading, you'll end up with a lot of shaded colors that you don't want. And so I find this polygon is a little better at doing specifically what I'm looking for. Alright, and when there's not much curvature, I can go a long distance between segments. When it starts to do some hard, fast curving, I put the points more frequently. I want this to be fairly accurate because I will double this as a source of graphic approximation of the area as well. Alright, so I've got the polygon. Put that tool away with an escape. Let me color it. So color, fill color, yellow. Okay. Now at this point, for me to continue providing just a graph of the region, I don't want to have a black polygon with all these black vertices all over the place. That doesn't look very clean. However, this polygon is exactly the item I want to use for the approximation part B of the problem. So what I'll do is I sort of I'm at a fork in the road, and I'm going to retain a second copy of this for part B. So I can go Control, view the pages of the document, copy, and paste. Okay, now here is back to page 2. Here's where I'm just trying to get the graph of the region. Now for this, let me go back to this polygon and go back to some more coloring. The line color should be yellow as well. There. Now the only thing are these distracting vertices of the polygon. I just go and hide them all. So it's a matter of going to them and hiding. Okay, starting to look very nice. Now the person reading this should be knowing just what's going on here, so let's make an effort to label this shaded region here as indeed the bounded region, as it's stated in the question. Part A uses the term the region bounded, so we'll call this the bounded region. Alright, this is looking pretty good now. The last thing that probably belongs on a graph of the bounded region would be these intersection points here. So let's go ahead and get those. Now I don't want the graph to be cluttered with 10 decimal place numbers for these, just something very basic. So why don't I go to the menu, the settings. Notice this is a graphs and geometry settings, not a document settings. So this is just for graphing, and the display digits, well, since I'm not sure how many I want until I see how complicated these are, let me leave it at float 5 and I'll come back and change that later. Let me first see how messy these numbers are. If they have numbers over 100, I actually would like to see 3 digits in that case. I want whole numbers basically. Okay, so to get intersection points, we can go menu and geometry, points and lines, and go with intersection points. Okay, graph 1, pick that one, and graph 2, pick that one. Okay, now that I see these numbers, looks like just 2 digits will be fine here for these labels. And so now I'll go to the menu and go to the settings, and here I'm going to decide for the graphing, just floating 2 will be fine. Okay, there. Now I have much nicer, simpler looking intersection points. Let me put away this tool and now move these to less intrusive locations. Okay, I don't want this to be on the graph, so let me try moving things to the right here. A little more. Okay, there, that point and this point are now pretty clear. I did kind of mess up the x-axis a little bit. Let me just put some nicer numbers on the x-axis instead of the negative 12.19 and 26.81 now. So let's go back to menu and zoom window, window settings, simple numbers like negative 12, tab, and 27. Click OK. Alright, there. This finally looks pretty good. I'll move that. Alright, now there's the graph of the region. It has about everything somebody's looking for when they look to see a graph. And now let's go to part B. We've got the basic region with its approximating polygon, which will be used as a source of approximation. How so? Let's grab the polygon, click on a context menu, go to measurement, area. Okay. 1.7 times 10 to the third. Okay, so that's times 1,000 in other words. Alright, so that'll be 1,700 in other words. And let's make a more complete label. So text, we can say approximate area equals. Okay, and there's a part B. Alright, so we can go ahead and also record this on our notes page, the summary page. Okay, so we've got our graph of the region is on page 2, and now we can explain what we've got going here on page 3. the area can be approximated with a polygon, and this polygon's area is about 1700. Okay. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Okay, using calculus to calculate an area, that means we need to slice up the region and sum the area of the slices. What kind of slices? Well, thin vertical rectangles are the most popular, and in our particular case will be the most convenient since we have a y equal to f of x type equation in both boundary cases. Alright, let's take a look and visualize to see if the thin vertical rectangles looks like a good strategy. The thin vertical rectangles look good. First, observe the tops of the rectangles. In each case, the top passes through a point on the F2 graph. Next, look at the bottoms of the rectangles. In each case, the bottom of the rectangle passes through a point on the F1 graph. This will make for easy formulation and one definite integral to calculate the area. Okay, let's take a look at a single thin vertical rectangle and informally formulate its area. First, its length or height. That would be the y-coordinate on the red graph minus the y-coordinate on the blue graph. That would be f2 of x minus f1 of x. Then, as far as the width of the rectangle goes, it's a little piece of x-axis. That would be a dx. So, the area of a single thin vertical rectangle would be the product f2 of x minus f1 of x times dx. Okay, so we know the thin vertical rectangles is a good strategy, and we know how to formulate the area of a single thin vertical rectangle. The other thing we need then is where to begin this sum and where to end this sum. We will begin the sum at the x-coordinate of the left point of intersection. We will end the sum at the x-coordinate of the right point of intersection. Those are our limits of integration. Once we have those, we are ready to formulate. Alright, so having decided on a strategy, let's describe it to the person reading our solution here. So we have a part C, and we can say that the area of the region can be calculated using a definite integral that sums vertical rectangles. We will need to get those limits of integration in order, and that's easy to do. We can go to our graph and we can store the x-coordinates into a1a and b1a respectively. Let's make a note of that here before, and then we'll go and do it. Okay, so we need to explain this to the person reading our solution, otherwise they won't really know what our integral is about. So let's go here to our graph of the region. Okay, this x we would like. Now remember, what's here is just the displayed number of digits. The Nspire really sits back and holds on to like 14 precision decimal places. So let's go ahead and click a context menu and decide to store this. Okay, so you might say A, because A is the traditional letter for a left-hand limit of integration, but the Nspire suggests we not choose single letters as variables, so let's move it to an A1. And then, because this is only a decimal approximation of the quantity, I will suffix it with another A to indicate approximation. Okay, so that's there. Same thing here for this one, except for this will be the B, which B1, because we don't want to use single letters, and then B1A because it's a decimal approximation. Context menu, store, B1A, enter. Okay, now we can return to our notes page and go to the next line, and we are ready to pretty much say area equals. Okay, let's go to the menu, calculations, calculus, integral. Okay, so left-hand limit of integration A1A, tab, right-hand limit of integration B1A, tab. We decided our thin vertical rectangles have area f2 of x minus f1 of x dx. So we have this quantity here. Let's just change that little triangle into a equals sign here. Actually, let's make it an approximately equals to, since we are distinguishing between parts C and E of this question. Alright, and another thing here would be to say square units. Okay. Well, what do we think about that? Well, we got a part D. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Well, let's look back at what we've got. Right here, just still in sight, is the 1704 square units. Our graphic approximation was 1700. 1%. 1% would be 17 unit difference. We're less than that, usually. So this looks very consistent. And we've got a very likely correct solution. So let's go ahead and say that. Thus, the solutions to parts B and C are very likely correct. Part E. If able, obtain an exact value for the area of the region. We could point out to the person reading this that the first step towards an exact solution is to get exact limits of integration. And I don't think I want to clutter this summary page with that. I will do that on a separate page 4, which we will use a calculator application. But let's at least point out what we're starting to do here. Alright, so now let's go ahead to page 4 and try that. So here we can control add a page, and let's go to a calculator. We're going to go with a solve, and it's f1 of x equals f2 of x, solving for x. Okay, success here. We've got these. And now something else we should do is we should start storing these while we're on this page as well. That's pretty easy to do. Now, which is which? Remember, when you get specific numbers out of the solve feature of the Nspire, the results are reported in ascending order. This one is our left-hand result. So shift and that selects it, enter puts it here, and then we can control store. Okay, and this will be A1 as opposed to A1A, which was our decimal approximation. Here's A1. Got it. Okay. Back up to get the second one. So shift select, enter to paste it on this line, and control store to B1. These are exact, so they just get the fundamental A1 and B1 names. And enter. Okay, we can go back to our notes page. So this was a success. See page 4. We could point out that the exact limits of integration are stored in A1 and B1. Okay, next we hope that the integration can also yield an exact result. And we could write area equal to, so we go to the menu, calculation, calculus, integral. Alright, A1, tab, B1, tab, f2 of x minus f1 of x, tab dx. You cross your fingers. Okay, got an exact result. And let's do a couple things. First, let's call this square units, and let's go back to this and make the math attributes so that that little triangular arrow is an equal to sign. Okay, there, we've got that. Thus, an exact area is achieved. Okay, and just one little item that may be making everybody uneasy, and that's, wait, is this the same as the decimal approximation? Otherwise, there's a problem. So let's go back here, and let's grab a hold of this. Well, actually, let's start a sentence of what we're about to do, and we can say, for additional peace of mind, we note that. Okay, let's hope this works. Gonna shift arrow left to select this quantity. Now here I have to go Control C to copy it. Back down to my sentence here. Control V to paste it. And now I'll go to the context menu. Actions, approximate. Okay, yeah, that was indeed the same as our decimal approximation from part C. So everything is in order here. Make a note of that. Let me get this box so that this is an approximately equal to. There. Okay, so that parts C and E are also consistent. All right, this has worked out real well.